Oh, well, Teams and Blackboard don't get along yet, so they don't upload automatically like Zoom did. So, it's been a headache, but I finally have updated everything. So they're all available now. And, I'll continue to do that. Okay. So getting into practicing doing proofs by contradiction and contraposition. For how many? I didn't write anything. So yes, I'll take it. It's okay. I got it. Don't worry. Okay. I'm hoping that we'll get into some set theory stuff today, but I think we still can even if we do a couple of these proofs. So let's do a few of them. I'm gonna try to pick proofs that are actually like difficult to do. That one's not. Are we okay to skip that one? Shall we do it? I'll do it. It's fast. It'll be fast. A lot. I had to take off on everybody's homework so far except for Jalen's, for not writing down the statement that you're actually proving. Got to do that. And your homework. Your homework should be legible. And so like I don't know. It's okay if it's more than one page. Okay. Yeah. Space your stuff out, man. I don't need to go find glasses or a magnifying glass to read your homework. The trees are already dead, okay? Yeah. And if you're that concerned about it, get an iPad and it that way. But I am. I'm a pro student teacher, so that's what that's about, and also what your homework's about. Yeah. Did he? Oh, he might have been on to something. It didn't take though. Not yet. He would ask you to redo it. That's awesome. Good. Okay. I've graded some messy work in my life, but it being squished together and messy is the thing that gets me. I can deal with one or the other. Both is hard for me to do. Hi. Don't be. Welcome. We're glad you're here. I was just telling them that I finally got all of our class recordings. They're up on YouTube now. They're on my YouTube channel. And so you can watch class from Tuesday. Okay. Homework 6, which is the worksheet in Blackboard, is going to be due this weekend. And then homework 7, our test is also moving. Yeah, I know. I'm really sorry. You missed a lot on Tuesday. The test on the schedule is supposed to be Tuesday. It's going to be Thursday. You should check. Yeah. Wait, I wrote this schedule down somewhere. Where did I do that? Do y'all remember? Rena, grab your phone. Nope, that's not it. There. All right. So we are in the middle of Now doing proofs by contrapositive and contradiction. So proofs by contrapositive, we are going to write down the contrapositive and then prove that. So we are going to do this now. We're going to let A and B be positive integers. Where A is bigger than the square root of n and B is bigger than the square root of n. Notice A times B be greater than root n times root n is equal n plus AB n equals A times B. A is less than or equal to root n. B is all this makes sense? Yeah. This means that A times B is greater than n, which means that A times B doesn't equal root n. So by contrapositive, if n does equal AB, then one of those two things is true, that A is less than or equal. Now, number two, we decided was a direct proof. I'm not going to do that with you because that is pretty straightforward. M is 2k plus 1 and n is 2l plus 1. Add them together. Move things around where you have 2 times an integer. Have 2 times an integer because it would be. Yep. That's pretty straightforward as far as proofs go. We went through the scratch work for this one, also a direct proof. It might be good practice for you to try to write these as like in full formal proof form, and then you can come to my office and ask me. Sound good? Yes? No? Whitney, what are you making that face for? Okay. Some of us need more practice than others of us, and we probably know who we are. And so if you are in a place where you are a little bit uncomfortable with some things, then I would probably try to write these up formally and then check yourself. Yeah. Number 3. Number 4, prove or disprove that the product of two irrational numbers is irrational. because you're disproving that the product of any two irrational numbers is irrational. To disprove a for all statement, you use a counterexample. You're right that we don't know what does it mean to be irrational, just that it's not rational, but we do know, we have proven that some things are irrational, like the square root of 2, and you know that the square root of 2 times the square root of 2 is 2, and 2 is rational, so that breaks this. As the product of at least two irrational numbers is rational, not irrational. How do we feel about number 4? Fine. Now remember, we have already proven that root 2 was irrational, and that is like the 4.8, that's the like big, those are the two big theorems, that there are infinitely many primes and that root 2 is irrational. And those proof structures are a thing that you should know. Okay. Now, number 5. 18. If n is composite, then n has a prime divisor less than or equal to root n. So if you try to prove this directly, you assume that n is composite, so then you come up with, it's composite, then it has two factors, A and B are between 1 and but you don't know that it has a prime divisor. Yeah. So we would like to either do the contrapositive or do this by contradiction. So what is the contrapositive of this statement? That would be our first step, is to figure out that. Yeah. Pause for a second. If n does not have a prime divisor that are equal to root n, it would be that every prime divisor is greater than. If it does not have a prime divisor less than or equal to root n, that statement is that if every prime divisor is greater than root n. Strictly greater. Because this is less than or equal to, and you are negating that piece. Greater than. Then what? What's the like statement for the contradiction? Right, this is if P then Q. What's the negation of that? Yeah, so the contradiction is the negation of the conditional, the negation of that implication. So that means that it's the P part and not Q. So for us here, that means N is composite and every prime divisor is greater than root n. So I'm not sure if you've picked up on this. I'm going to do a proof of contradiction because that's my favorite way to do proof. We're going to suppose not Suppose N is composite and every prime divisor since N is composite, N is equal to A times B for some integers A, B. Strictly less than A or B, but strictly less than N. Did we just for a second ago? Six. If n equals a, b, where a and b are positive integers, then a is less than or equal to root n, or b is less than. Okay, so oh my lord, I got it. We're good. We're fine. It's in the, I was like, this doesn't make any sense, but it's because we're doing a contradiction proof. Duh, it's supposed to make sense. Um, uh, A and B, they aren't necessarily prime divisors, but the prime divisors would be inside of them. So that means that A and B are also both greater than root n. But this is this is a factorization of n. Yeah. Every prime divisor is every prime divisor is greater than root n. These guys are either prime divisors or they contain prime divisors. So they are both greater than root. Yeah. If this was a bunch of primes, P1, P2, P17, whatever, right? A contains these and B contains these guys. Yeah. Then A and B are either prime divisors themselves, so greater than root n, or they contain prime divisors in a product, so they are both greater than root n. A is greater than root and is greater. But B times B and is greater than n equals A times B, which is greater than root n times root. Contradiction. A prime divided. I got stuck in there. Bad. Okay, again, N is composite, so it has a factorization, A, B, where A and B are strictly between 1 and N. This is because it's composite. It wasn't composite, right? Because then your factors could be 1 and N itself, but they've got to be strictly in between there for it to be composite. And then our assumption that every prime divisor is greater than root N gives us that each A and B are greater than root N. Either they are prime divisors themselves, or are products of prime. And then looking at this like string of what should be a string of equalities or inequalities that makes sense, it contradicts itself because N is A times B. Establish that. But A and B are both, and so this product is greater than root N times root N. Then greater than it. So that doesn't. So must be the original statement. Yeah. That makes sense? A little bit? Maybe? Okay, good. Like to give me any feedback? Fine. Yeah. Proof would be the same. I mean, really similar. Every prime divisor is greater than root N. Oh, no, I don't even know how you would do that. I don't know how you would. Yeah, no, I think if you tried to do that, you would arrive at a place where you need to do contradiction, so. But one of the notes in here says, like, sometimes when you try to do proofs by contrapositive, you end up, like, can't, get stuck. Okay, this next thing, I remember yesterday, no, Tuesday, when I was like I was flipping all through my pages trying to find this place where we did this thing. Also would have been useful. We all got that homework, right? So it's okay. On your homework, whatever, let's just do this. Okay, P is prime, and P divides some product of things. Then P divides one of the pieces. Now, we have been using this a lot when we did our, like the proof that root 2 is irrational, right? We got to the point where we were saying this thing, and I was telling you this works because 2 divides A. Oh, but 2 divides A squared means that 2 divides A, that's because 2 is prime. Yeah. We did the same thing with like 3 divides B cubed. Well, 3 has to divide B again because 3 is prime, so it goes into one of those factors of so the also this was the 12A equals 25B thing that y'all did on your homework. And the question was like, does 12 divide B? Does 25 divide A? The answer is yes. And it's because of this this idea here, the here it is. So 12 is 2 squared times 3 to the first times A, and then 25 is 5 squared times B. Because of the like prime factorization here, the 2 squared and the 3 to the first, that has to be contained in that B. Because it's not sitting in the 5 squared, and the 5 squared has to be sitting inside that A for these things to be equal. So that's sort of how that works. The idea here, and like this sort of thing is true, like you're looking at 3 divides A times A times A or something, that means that 3 divides just one of those A's. But these are your, like, 3 of these guys. Now we're gonna prove this, or we're gonna actually prove what is called Euclid's lemma. It is a, like, condensed version of it. But it does introduce a good proof method, so that's good. So we're gonna prove Euclid's lemma, which is this. A lemma is a thing you use to do a proof. Euclid's lemma says that if P divides A times B, then P divides A, or P divides B. Now, you guys had this thing on your homework where you were trying to prove something like this, but you did not have the additional expectation that the P was prime. On your homework, it was A divides BC, divides the A divides B, or A divides C. That is only true if the A is prime. Yeah. So that is not true in general. With some examples where it does not work. But anyway, if P is prime, then it does. That prime has to go into one of those 2 factors. It can't be split between 2 of them because it's a prime number. So it doesn't have any factors itself. So proof-ish. We are going to suppose that P divides AB for some prime P. And integers A and B. The fact that we were trying to show that P divides A or P divides B, I'm going to suppose, without loss of generality, that P does not divide A. That P has to back in. So I have this thing that's true, P divides A, B, and the concluding part of that is that either P divides A or P divides B. We're going to assume that P does not divide A, so it has to divide B. Now, the assuming without loss of generality means that I don't have to do that both ways. I don't have to also show you, well, suppose P doesn't divide B and show that P divides A. The thing is that I'm just choosing, and it doesn't matter which way that I choose here to say it doesn't divide one of them. But the proof would be the same. So you do this thing where you do, I'll write it down. You use this thing, log, for without loss of generality. Suppose that P does not divide A. That's the vertical divides bar with a knot through it. Okay, now we have P divides AB. So by definition, what do we know? WLOG. What did you think it was? The other letters maybe. Okay. This is log for without loss of generality. Stop saying stuff like that. What does it mean? that AB equals P times K for some integer K. Yeah, that's the thing we can actually work with. We can't work with the vertical bar. Yeah. Vertical bar gives us a definition, but we can't do anything with the vertical bar as is. Yeah. So by definition, AB is equal to P times K for some integer K. Watch this, y'all. AB over P. Now, I know we're not allowed to divide, but stick with me. Well, P is a prime number, so it's not 0. We're allowed to divide. Right? In general, we can't, but P is a prime number, so it's not 0. Yeah. So we're not going to break anything by dividing. Now, here's where we need to be careful. This thing is what's happening, right? AB divided by P is A times P, B over P. Whoa, I don't know if I said those letters right the first time. AB over P is going to be A times B over P, and this equals K. Now, A is an integer, B an integer, P prime also an integer, K an integer. We good? Okie dokie. Now, A is an integer and K is an integer. B over P has to be an integer. Which means that P divides. A and K are integers, and P does not divide A. It must be that P over P is an integer. So P divides B. This P is a prime number. Oh. Yeah, that's fine. P is a prime. So the only way that so B was an integer to begin with, so B1 would still be an integer. But P is prime. Right. You're doing the proof. So that statement in general, like a thing dividing a product means that it divides one of the pieces of the product. That's not always true, unless the thing that's dividing the product is prime. Right, again, on your homework, you should have disproven that if A divides BC, then A divides B or A divides C. I think, for example, did you find something with a 6? What's your homework? You have your homework right there. Yeah. I don't know. It's the third from the last. Second or third from the last one. A is 6, B is 9, and C is 4. The thing is that 6 divides 36, but 6 doesn't divide 9, and 6 doesn't divide 4. Right? And that's, again, because 6 isn't prime. So you can break up its prime factors to the two other, between those two things in the product. The example we did, Whitney, was what, 20 and 4 and 10? That A is 20, B is 4, and C is 10, right? You've got the prime factorization here, so this is 5 times 2, this is 2 times 2, right? This is 5 times 2 squared, right? So the pieces of that thing are broken up into the parts of the product. Well, if it's prime, that can't happen. If it's prime, then it, gets eaten by one of the pieces of the. That okay? Any questions about that? Oh, you're okay? Now, y'all saw me use this in these two things that we've done right here, Euclid's lemma, and also this are things that we used when we were doing our proofs. It's 4.7 that we did our proofs. Shoot. I mislabeled the videos in YouTube. I'll have to rename them. I have 4.8, but we did not do 4. But it has a date on it. So. I need to read. Wait, no, it is. 4.8 is what it is now, right? What section is numbered 4.8 in your notes? The classical theorems. You are fine. The textbook notes I'm looking at has the algorithms marked as 4.8, but that's 14, right? Yeah. Okay. Algorithms, 410. That's where we are right now. I did label it correctly, Marina. Don't you even worry. And it has the date on it. Okay. The Euclidean algorithm is a way to find the greatest common divisor of two numbers. Now, remember when we did our proofs for the square root of 2, for things being irrational, one of our assumptions was that the GCD of the two things was 1, or that the two numbers are relatively prime, that they have no common divisors. So this is kind of cool, if I'm being honest. I mean, it's sort of tedious and annoying, but it is cool that remember, this is the fundamental. Nope. The quotient remainder theorem, because this got a quotient and a remainder. Look at that. The quotient remainder theorem says you can write any integer like that any integer a can be written as bq plus r, right? That's the quotient remainder theorem. You good? Yeah, you are good. This is from, whoa, this is from the quotient remainder theorem. That's where this thing comes from. Any integer can be written that way. Now, the Euclidean algorithm adds onto that. Well, if you've written the integer like this, then the greatest common divisor of these two numbers, a and b, is the same as the greatest common divisor of b and r. And no, that's a little bit crazy. So, like, what happens then is you get this, like, it's called an algorithm, because you apply this thing and you do it again and you do it again and you do it again until you get the thing. Cool. So the GCD of 12 and 18. Now I want us to write this as that 18 is equal to 12 times something plus a thing, right? Yeah. 12 times 1 plus a remainder that is between 0 and 12. So the remainder is 6. Yeah. So the Euclidean algorithm says, well, the GCD of, I'm going to write that as 12 and 8, as 18 and then 12. Is equal to the GCD then of this value, 12, of this value and this remainder. So what we're going to do then is the same kind of idea. We're going to set this up again, that 12 is equal to 6 times a thing plus a remainder. So that's a 2, and then the remainder is 0. We good? So this would be equivalent to the GCD of 6, 0, which is 6. Good. Nothing. Um, the Euclidean algorithm would be useful in number theory type things. But anything that's got Euclid's name attached to it. That's what it does. The GCD of 201 and 111. I'm going to figure out the Euclidean algorithm. We don't really do anything except talk about it. I guess that y'all just feel like y'all need to know it for something on the, or Dr. Dawson wants you to have seen it before you get to your algebra theory. You would use this on the computer science exit exam. If you're doing cybersecurity, you have to be here. If you were going to pull a math minor with it, you'd use it in linear algebra. Are you going to take linear algebra? No. Could do a math minor, which is like 2 more. No, thank you. Okay, so the GCD of 201 and 111, again, we're going to sort of set this up the same kind of way. I'm going to draw a line here so I have some separation. So we have 201 is equal to 111 times a thing plus a remainder. I'm going to go ahead over here, the GCD of 201, 111. And notice, I mean, this sort of follows this pattern, right? The 111 is going to go here. Whatever we get here, we'll go in the next one. Okay, so we can't multiply 111 by more than 1, so no. What is that, 90? And then we're going to move the 111 over here and move that 90 here. So 90 times a thing plus a remainder. Four, 6. Are y'all with me or not with me? One is 6 times 3 plus 3. Basically, you want to follow this like trail down. You're going to just sort of this rabbit until all the way gone. Once that remainder is 0, whatever that like divisor is. I would think that as computer programming type people, that this sort of thing would be appealing to. What? What? it is the remainder that very last time that there is a remainder. Yeah, and that's the greatest common device. Yeah. 3 is the biggest thing that goes into both. So those two numbers are not relatively prime. Yeah, anything that's divisible by 3, it's digits, RA multiples. That's a stupid trick with these. You know what I don't like? All the like songs and things to memorize tables or like tricks like that. I don't know. Like, are we really understanding what we're doing when we do that kind of thing? People who memorize the unit circle really irritate the crap out of me. Haley knows this, but like when people start shouting things at me like 1, 2, 3, 3, 2, 1 for the unit circle, I'm like, I want to not ever hear you do that again because that shows you don't actually understand anything that's happening. You've memorized a pattern, and that's not understanding things. Y'all need to hear that today. Marina, it's been a while since you heard me get irritated about that, huh? Didn't think you would today, but my pre-cal students have a test on Monday, and I've seen them do it recently, so it's fine. The Euclidean algorithm, we are going to do this. We are going to let A, B, Q, and R be integers where it fits this, the quotient remainder theorem. So let A, B, Q, and R be integers. This is kind of a cool proof. That's probably why we're doing it, because the proof is cool. Such that A is equal to BQ plus R. Say by the quotient remainder theorem, if you're really feeling it. I'm going to suppose that the GCD of A and B, integer M, and the GCD of B and R, integer N. Now, again, remember the Euclidean algorithm, which is way up here. What we're going to prove is that M equals N. You with me? We have assigned this as M and this as N. Yeah. We are going to prove that those are the same. Okay. What does it mean for the GCD of A and B to be M? The greatest common divisor, at least a divisor, right? And that gives us something to actually work with. You good? So if the GCD of A and B is M, we have that M divides A and M divides B. Like 3 divides 2 or 1. So by definition of that, we have that A is M times K and B is M times L for some integers A and L. A lot of letters floating around in this proof. Some that mean things and others that mean different things. Okay, so A, B, Q, and R are integers, so that A is equal to BQ plus R by the quotient remainder theorem. We can do that. Suppose that the GCD of A and B is M, and the GCD of B and R is N. So since the GCD of A and B is M, we know that M divides A and M divides B. We'll get to the GCD of B and R later. Because M divides A and M divides B, we have that A is equal to M times K and B is equal to M times L for some integers K and L. Okay. Notice A is equal to BQ plus R, that we had before. A is M times K and B is M times L. So we're looking at this thing. Now I'm going to move that stuff over. So MK minus MLQ equals, factor out an L. Okay, what does this mean? M divides R, but yeah. Yeah. So since the inside there, K minus LQ is an integer, have that M divides R. Okay, yo, what we have right now is that M divides B and M divides. How is that related to? If N is the greatest common divisor and we just found a common divisor, this common divisor has to be less than or equal to N, right? It's either just a common divisor or it is itself the greatest common divisor, right? Yeah. Since M divides B and M divides R, M has to be less than or equal to N, d of. Okay, and then we're going to go with this sort of similarly. N divides B and N divides R, so B is N times X, and R is N times Y. Notice A equals BQ plus R. We have B is N, R is NY. Oh, we should. Yeah. Since XQ plus Y is an integer, what do we have? A. Divides A and N divides B. N has to be less than or equal. Yeah. The GCD of A and B is M. We found a divisor. It's A. I mean N. So N has to be less than or equal to M. So the GCD of A and B equals the GCD of B and R. I'm gonna zoom out to get the whole thing. You want me to So the thing we assumed was that the GCD of B and R is N. Then the fact that we have that N divides B, and then we get that N divides A. So because N is a divisor of both A and B, it has to be less than the greatest common divisor of A and B. That means that N is less than or equal to M. Yeah. Yeah, and then up here, when we were doing this before, we have M divides R and M divides B. Oh, so the GCD of B and R is N. That means that M is less than or equal to N. Since they're both less than or equal to the other, they have to actually be equal. Any other questions? No? It's a cool proof. Kind of weird. Fun. Now, for some maybe more lighthearted things, bit. That's y'all know about sets, I think, maybe some about sets. We have been using sets of numbers thus far. A set is an unordered collection of objects called elements or members. I'll be calling them members. I will call them elements of a set. So the sets we have used so far are the real numbers, which are basically any numbers that don't have an I in them. The integers, which, you know, we have been using, but remember are just these guys. Irrational numbers are the set of all M over N, where M and N are both integers and N doesn't equal 0. For natural numbers, these are what are called the counting numbers, like what you would teach a child. So one starts at 1, 2. When you teach a kid how to count, those are your natural numbers. And we also call that in this class, we'll call that Z plus. Now the thing that gets me, and if y'all write your zeros like this, stop. This is the empty set, so it is the set that actually contains nothing. So it's brackets for a set that there's nothing inside. Don't write zeros like that's the empty set, not a 0. The null set, what do you guys call this in computer science? Yes. So it's the set that contains nothing. Doesn't contain the empty set, it actually contains nothing. Okay. The notation we've been using this kind of all along, and sorry about that, but the notation for an element of a set is that little e. We've been using that, right? When we were doing domains and things, domains are sets. So this is an element of, when you put a line through it, it means it's not an element of. So we're going to list the members of these sets. We're going to list the elements of these sets. Set of all X. This vertical bar, y'all, is a such that. When you're reading that, read it as a such that. This is a set of all X such that X is a real number such that that's terrible. X squared equals 1. So we want all of the numbers. Yeah. Side of a set. So like if it's written like this, it's a such that. If it bothers you, huh? If it's inside of curly brackets, unless it's in. You'll know. I can also use colon such that if you would. I don't think that you. So we would like to know all of the real numbers who square is 1. And negative both squared to give. Those are curly braces. They don't really look like it, but that is what those were supposed to be. I'll tell know that I have a student who exclusively uses absolute value bars for his parentheses. Oh. Everybody's not telling me. I keep writing on every. Hasn't worked. Okay, so the next set is the set of all x such that x is the square of an integer and x is strictly less than 100. The b equals beginning curly brace. I was just trying to give names to these things in alphabetical order. In a minute, we're going to talk about the cardinality of these things, and we're going to wait for the set. So I'll just go in. Y'all, this part's not supposed to be hard. What are perfect squares? Name them. Perfect squares. Also 0, but yeah, 1, 4, 9, 16, 25, 36, 49, 64. Good. Woo! And we're done. Good job, everybody. We are going to determine if these things are true or false. We're trying to get comfortable with notation before we start writing proofs with notation. So, everything that we're doing in here is to eventually write a proof with it. Oh no, not in a formal proof. You can't use notation. Not for me. Some people will let you get away with it, but all right. I might let you do this at some point, but not yet. We gotta be formal right now. Y'all are having trouble with being formal at all, so I'm gonna dig in until you do it, and then once you're doing it, maybe I can relax a little bit, you know. I gotta really go all in until you get used to it. This is really real. Formal proofs mean they should look nice. Yeah, right. It's a final draft of your argument. Yeah, it should look. Okay. True or false? 2 is an element of the set of all integers. Cool. 1/2 is an element of the set of all integers. False. -3 is an element of the set of rational numbers. 5/3 is an element of the set of rational numbers. -2 is an element of the real numbers. Pi is an element of the real numbers. That's true, folks. That's true. Doesn't have an I involved, right? Real numbers are anything that's not imaginary. Pi over 2, rational number. That's a no. An integer over an integer, right? That's what it means to be a rational number. It's a ratio of 2 integers. But pi is not an integer, so it does not work. -2 over 1 as a natural number. That's a negative. Because it's a negative, yeah. Natural numbers are your counting numbers, 1, 2, 3. Okay. So Now we have different notation that looks similar. You see the little C's there? Those are subsets. That's a subset notation. So that's about full sets, not pieces of a set, okay? So, well, the the set A is a subset of B that's written like this. That's the subset notation right there. A is a subset of B. If every element of A is also an element of B. So I read these as because it's a B when I read them, and hopefully you will get to this point too, where you're saying contained in. So think about it like that. Is this set contained in this other set? So, there is a chart online for how you can, there's a chart in my Math 105 notes too for how this starts. Natural numbers, whole numbers, integers, rationals, reals. Anyway, are the integers contained in the real numbers? Is every element of the integers also an element of the real numbers? Yes. Is every element of the integers also an element of the rational numbers? Yes. Is every element of the integers also an element of the natural numbers? This one's a no. Is zero an element? Look, that's an element notation, not a subset. Is zero an element of the empty set? No, there's nothing in the empty set, not even zero. Okay, so these are about to get weird. Number 5, is the empty set an element of the set containing 0? No. It is not. Is the empty set a subset of the set containing 0? Well, the definition of a subset is that every element of the set on the left is an element of the set on the right. Every element of this, which is nothing, is contained in this because it's something. Empty set is a subset. The empty set is a subset of every single set. Right. Nothing is also in nothing, so it's a subset of itself also. Yeah? Nope. Is X an element of the set containing X? Number 8, weird. Is the set containing X an element of the set containing X? No. Is it correct? Then the sets are like arrays. On this one, if this was written like this, is the set containing X a subset of the set containing X? That answer is yes. Yes. Yep. Every set. Yep. Every set is a subset of itself. But yeah, what Charlotte's getting at is if we sort of like rewrote this as if that set, if I had X, I could say that X is an element of the set containing, I don't know, the empty set and the set containing X. You get what is happening there? If you can see it sitting there, then it is an element. But you see this set, gosh, you can't see that because it's written like a kindergartner wrote it. Let me work on that. The set containing X is an element of the set containing, I don't know, 3 and the set containing X. The two elements inside of this set are 3 and the set. That is actually an element. Set containing. Okay. Yeah. So this definition that A is a subset of B, how would we do that in like symbolically? Remember, the definition is that it's the subset of every element of A is also an element of. We would like to have an if P then Q thing so that we can prove stuff, yeah? We should. For all what? Okay. Little a, big A. For all A, if capital letters sets, little lowercase letters are elements of sets. Yeah, X is so fine. We're going to do this often. We will call the elements of the set the lowercase version of that set so that we know where it's coming from, because we're gonna do this with functions too, like f of A. Knowing that A started in big A is gonna be important. No, no. And when I teach this in 105, I actually tell them to think about it that way. It's like less than, it's contained inside of the thing. Yeah. That's fine. Okay, so if we were writing a proof for these, which we won't have time to do today, but let's suppose we were gonna write a proof, how would we do this? When we do it for all proof, how do we do that? Because we can't show it for every single one, right? We just pick an arbitrary element, yeah? So we would pick some arbitrary X in A. And show that it's in B. You're like into the Venn diagram thing, A being a subset of B looks like this. What computer thing are you talking about? I have no idea. So on Tuesday, when I see you again, which is going to be the day before your test, which is, well, I mean, the class before your test, which is on Thursday. All right, with me. Everybody's with me. Yes. We have started chapter 6 now. Yes. Oh, before we go, Lord, may not, but that's fine. We can test 3. We'll just do what we can on Tuesday. I'll see you guys then. We'll talk about that homework too. See if you can do any of the homework for Tuesday, before Tuesday. That didn't make any sense. Before tomorrow, no, before Saturday night, you need to turn in homework 6, which is the contradictions and contrapositive worksheet that is in Blackboard. Yeah? Okay. And before Tuesday, you should look at the chapter 6 homework to see if you can do any of it. Good? Okay. Have a great day. Homework 5, I did. I will grade it today and email it tonight. Yep. I got it. Thank you. Yes.
Are you talking about that writing all?
That's a good idea. That's a very good idea. Yep. Yep.
Just having like that. That it's.
Yeah, until it becomes, oh yeah.